for section 7. This is our last section of chapter 4, which we've been talking about graphing linear functions. So it makes sense that we're talking today on our last unit about graphing piecewise linear functions. Now, piecewise is literally just pieces of linear functions that are graphed on the same xy plane. So let's take a look at what an example of a piecewise linear function would look like. So we have a function f of x is equal to, now notice that it opens up with this brace, and now there's a couple of equations listed with commas and then this interval notation. All right, well, over here on the left, these are your actual functions. These are the pieces of graph that you are going to place on the xy plane. After the comma are your domain restrictions or your domain intervals. Okay, that's where you're going to graph those branches. So I color-coded it here so you could see. We're going to graph the equation x minus 2 where all x's are less than or equal to 0. Now, where x's are less than or equal to 0, if you're looking on your x-axis, your number line, that's your negative x's. You got negative 1, negative 2, negative 3, and negative 4. So we're going to graph that to the left of that y-axis. The orange graph here is the 2x plus 1. We're going to graph that to the right of where x is greater than 0. I should say we're to the right of the y-axis where x is greater than 0. So here is x is equal to 0. Here's 1, 2, 3, 4. So that's this orange domain. All right, so you can see here we've got an open circle, and then we have a slope of 2 and a y-intercept of positive 1. Likewise, over here on the left, our graph, we have a y-intercept of negative 2 with a closed circle and a slope of positive 1. We rise 1 and move to the right 1. So there is an example of a piecewise linear function. You have two pieces in this case. Sometimes you'll have 3 pieces, 4 pieces, or 5. And you have different domain intervals over which you're graphing those functions. All right, let's evaluate a piecewise function. Now this is exactly the same piecewise function that we have above. And so we can use the graph here. But we want to evaluate it when x is equal to negative 1. In other words, what is f of negative 1? Well, the trick here is understanding which one of these two equations to use to evaluate it. And because x is equal to negative 1, that falls in this first domain interval because negative 1 is less than or equal to 0. So we are going to use this first equation, x minus 2. All right, so we're going to say negative 1 minus 2 because our x value is negative 1. That results in negative 3. So we would say f of negative 1 is equal to negative 3. And you can confirm that by looking at the graph here. Here's where x is equal to negative 1. We go down to the graph, and there's the output at negative 3. All right, likewise, let's evaluate f of 1/2. Again, you want to ask yourself, which one of these two equations, or the two pieces, am I going to use to evaluate f of 1/2? Now, because 1/2 is greater than 0, that's the domain that's in the orange. All right, so we're going to use the function 2 times 1/2 plus 1, and that will result in half of 2, which is 1. 1 plus 1 is 2. So we would say f of 1/2 is equal to 2. And again, you can confirm that by going over to the graph and checking out where x is equal to 1/2 is right here in between 0 and 1. And then going up to the graph, the output there is 2. All right, let's get some practice at graphing a piecewise function. Now let's take a look here, and we see our two pieces are the graph negative x plus 3 and x minus 1. Our domain now is a little bit different. Our domain intervals here are x's that are less than or equal to negative 2. So you can see I highlighted that here in yellow. And then I have x is greater than negative 2, and that's the one highlighted here in orange. So let's start off by graphing the domain in the yellow. So that's my graph y equals negative x plus 3. I have a slope of negative 1, and I have a y-intercept of positive 3. But I'm only going to graph that in the yellow domain. All right, so my y-intercept of positive 3 would be right here, but that's in my orange domain. and I have a slope of -1. All right, that means if I go down 1, I would move to the right 1, down 1 to the right 1. Or if I move to the left 1, I would come up, and then to the left 1 more and come up 1 more. Aha, now I'm on that border of the yellow and the orange domains. All right, now because this graph includes -2, I'm going to have a closed circle there. And I'm going to plot my next point. To the left 1, up 1, to the left 1, up 1. And I can connect those 3 points. And there's the graph of -x plus 3 over the domain where x is less than or equal to -2. All right, now we're ready for that bottom function. We have the equation y equals x minus 1. And that means that we have a slope of +1 and a y-intercept of -1. All right, and we're going to graph this one in the orange domain. All right, so my y-intercept here of -1, well, that's good. That's in the orange domain, so I know that that's a point that's on the graph. And I have a +1 slope, so if I rise 1, run 1, that point will also be there. Rise 1, run 1, so on and so forth, all the way through that orange domain. However, I got to keep going back until I get to that border of where yellow meets orange. So this point here will be on there. And then finally, I got one more point, but this is going to be an open circle. And it's an open circle because it's all the x's greater than -2, but not including -2. So now if I connect all those points with a nice straight line, here is the graph of y equals x minus 1 over the domain where x is greater than -2. There you go. You graphed your first piecewise linear function. All right, example 3 now. We're going to give you the graph at the right, and I actually color-coded your domain intervals for you. But now we have to write the equations, and we're going to write those equations out in slope-intercept form, mx plus b. All right, so to write this, we're going to start off with an open brace, and then we're going to leave some room for our functions, and then we're going to list our domain intervals after the commas. All right, so our first domain interval, let's take a look at this yellow one. It's going to be all the x's less than or equal to -2. Right, and it includes that -2 because there's a closed circle there. Then our next domain is this orange one. It looks like it's going to go from -2 to +1, but they're both open circles. So I want all x's that are greater than -2 but less than +1. Finally, our last blue domain here are going to be all the x's greater than or equal to +1. All right, now it's time for us to start talking about the functions, listing them out in slope-intercept form. So we need to know our slope and we need to know our y-intercept. Let's start with the yellow domain. It looks like we have a slope of -1. If I go to the left 1 and up 1, then that's coming down and to the right, and that's going to be a negative slope. So that's a slope of -1x. Now let's get our y-intercept. If we were to continue this line, it looks like it would pass through -2 on our y-axis. So -1x minus 2 is our function. Next, let's do the equation in the orange domain. This is a horizontal line, so my slope is 0. And we're just going to write it out as 0x right now. And my y-intercept looks like it passes through 2, so y equals 0x plus 2. Now, in the future, you don't need to write 0x, but we're just doing that so we can see that it has a horizontal line and a slope of 0. Our final one is our blue domain here. And again, we're going to count our slope. It looks like we're going to rise 2 and run 1, so that's a slope of 2. And if we were to continue that back, it looks like it would pass right through this -3 on our y-axis. So this is the equation y equals 2x minus 3. And there you go. You wrote all 3 functions over the given domain intervals. So think about color coding those different domains, and that might help you to see what those domain intervals are. All right, for our final part of today's notes here, we have a step function. A step function is just a piecewise function and it's defined by a constant value over each part of its different domain. So you can see why it's called a step function. It definitely looks like steps. And in this example, we have the function f of x is 2 when x is greater than or equal to 0 but less than 2. And as soon as it gets to 2, it's going to jump up to 3 until x is less than 4. And as soon as it gets to 4, it's going to jump up to 4. So on and so forth. So that's why this is called a step function. All right, so we're just going to simply introduce to you what a step function looks like, but we're not going to do much with step functions today.